Air flows into the atmosphere from a nozzle and strikes a plate. Here is the plate right here. And you can see we've got air coming out of here. It's going to come up and down, and it's coming out of that nozzle. We're given the area of the nozzle. It's 0.003 meters squared, and then we've got the area in the tank basically, which is 0.01 meters squared. And here's our pressure gauge up here. So we have a force of 12 newtons that's needed to hold this plate in place as the air strikes the plate. We want to determine the reading on the pressure gauge, and we're going to assume incompressible and frictionless flow. Alright, so keywords here are incompressible and frictionless first of all. So we know if we have that type of flow, we have our Bernoulli equation that we can use. So that's going to simplify things. So I've written down Bernoulli's equation right here. You can see it. So again, that's just a relationship between the pressures and the velocities, and then our density is going to be constant because again we're incompressible. Now first thing we want to do is simplify this if we can. So if you notice here we've got gauge pressure. So anytime we have gauge pressure, we're going to say that our atmospheric pressure can basically go to zero, right, because we're taking out the effects of that. So on here you'll notice I've got these markers, the 1, 2, 3, and 4. That's just denoting which section. So if we look at pressure 2, so that's going to be right outside of the nozzle, we're going to say that this pressure is going to go to 0. And we're going to say that because we want gauge pressure, not absolute pressure. Alright, so let's make that simplification, and let's see where to go next. So now we need to know how to relate the velocities at point 1 and point 2. Now the way we're going to do that is continuity. And remember, that's conservation of mass. So for the continuity equation, we're going to say that Q1 is equal to Q2. So let's write that out. So we're going to have A1 times V1 equals A2 times V2. And let's solve this equation for V1. So V1 is going to be A2 times V2 over A1. Now we're going to plug this equation here for V1 back up into Bernoulli's equation. Right, and we'll use that equation in just a second. So let's come over here and do that. So we're going to have P1 over rho plus A2 V2 over A1. Let's square that. That's going to go over 2. And then that's going to equal V2 squared over 2. Let's call that equation 1. Now let's hang on to that for just a second. And let's see what else we need to do. So we were told that we have a 12 Newton force that's required to hold that plate in place. So somehow we need to use that 12 Newton force to figure out our problem. And the way we're going to do that is conservation of linear momentum. So remember, anytime we have a force, just think linear momentum. Alright, I've written out the equation. So we've got the summation of forces on the left, and then we've got our two integral terms on the right. Now this first one is doing the partial with respect to time. We don't have anything changing with respect to time, so let's go ahead and make that term go to 0. And that's going to leave us with this second term. So we're going to have the integral of the velocity vector times the density times the velocity vector dotted with that little unit vector n times dA. Okay. Now let's go ahead and look at our velocity vectors and n. So let's look at v2. So that'll be the velocity right outside of the nozzle. That is going to be v2I. And then n, remember, is going to go out of the control volume. So let's scroll up here for a second. So if we make our control volume something that looks like this, then that would mean that our n is going to go out like that. Okay, so n for section 2 is going to be negative I, right? And then let's do v3 and then v4. They're going to cancel each other out, but we'll do it anyways just so you can see how to do it. So v3, we're going to say that that's negative v3j, and then n for part 3, will be negative J. I'll go up to the drawing in just a second to show you that. And then V4, that's going to be V4 times J. And then N for that section would just be a positive J. So let's go back up and look at that. Actually, I have these numbered differently than I have on my notes. So let's make this one 3, and this one's going to be 4. Sorry about that. So if we switch that numbering around and then we draw in here. For 3, we're going to have flow coming out this way. So N needs to go outside of the control volume. So let's put it in the negative direction. And then up here at 4, our flow is going out. And N will go outside of the control volume, so that's going to be positive. And that's how we get these signs here for N. Okay? So just remember N is always going to go outside of the control volume. Alright, so now that we have that, let's get back to this equation, our linear momentum equation. We know that the sum of the forces is going to be 12. We're going to deal in just the x direction. Alright, and we're doing that because our force is in the x direction. So if we do that, let's put negative 12 because it's going to the left. So that's a negative I unit vector. And we're going to set that equal to V2 times rho times V2 dotted with N2. So if we have that, we'll have V2I dotted with negative I. And then we need times the area. Now the area at point 2 is 0.003. So just write that in. So that is going to leave us with negative 12 equals V2 times rho times negative V2 times 0.003. Alright. And again, we're not using this V3 and this V4 because those are in the y direction. So we don't have any forces in the y direction, so we don't need to worry about those. Alright. Now let's simplify this equation. If you do the calculations, you'll get 4,000 over rho equals V2 squared. Okay. And we can plug in our density. So we'll have 4,000 over 1.23. That's going to be the density of air we're using. And that gives us 3,252.03. Right? And that's going to be V2 squared. Right? So you can come through here and then solve for V2, and you'll get 57.03 meters per second. Now remember, what we're looking for is pressure. We want that P1. So we're going to come back up to this equation 1 up here, right here, and we're going to plug in what we know. Alright, so let's do that. Last step. So from equation 1, we're going to have P1 over the density, which is 1.23, plus the area, which was 0.003, times the velocity of V2, so that's 57.03, and then we're going to put that over the other area, which was 0.01, and then we are going to square that. And we're going to put that whole quantity over 2, and we're going to equal that to V2 squared. So that's the 3252.03 over 2. And if we do that, do the simplifications, we get that the pressure at point 1 over 1.23 is equal to 1,479.66. So the pressure at section 1 will be 1,819.98 pascals. And that will be your pressure read by the gauge. Okay. So that's an example of how to combine the Bernoulli equation with the conservation of linear momentum.